Cool. All right. Well.
Right. So I think we can you can leave it in share mode if you want, or you decide. But okay, so recording has started. So okay, so maybe let me say a few words to introduce our speaker today, Dave Schuster from the University of Chicago. So Dave and I met some years ago now, when he was a PhD student with Rob Shalkoff at Yale, where he worked on the first experiment together with Andreas Wallraff, the first circuit QD experiment, and has been working in this field from that point. So Dave is one of the most creative physicist slash scientist slash person that I know. He always has a ton of new ideas. And what is great is he tries these new ideas and they work. So if you look at his group webpage, you will find work on stabilizing many-body states in superconducting circuits, or looking at coupling spins with microwave photons. Electron on helium has been one of his interests. Trapped ion also for a while, right? And now you will talk to us about detecting dark matter axions with superconducting qubits. And with that, I'll let Dave present his talk.
Let's see. Thank you so much for that overly kind introduction. Let's see. Yeah, it's kind of funny because I feel like at least half, or at least most of the good ideas probably came from you. Anyway, but yeah, so yeah, this is a kind of something I didn't expect to get involved with when I was starting my lab, but we're very close to Fermilab. And I don't exactly remember how, but I somehow ended up talking with Aaron Cho here, who's heavily involved with ADMX, which is a search for one of the types of dark matter. And so he sort of wrote me in. So I'll tell you a little bit about kind of the basic problems and how we do things. So just by way of an outline. So I won't talk too much about dark matter and what it is, because I don't actually know that much. I guess no one does, but I know less than most. But I'll tell you a little bit about that and how people are currently trying to detect it. And sort of the upshot is that we're going to try and use our superconducting qubit technology as a photon counter, and the real challenge with these, I guess all dark matter experiments is, right, you're essentially trying to lower the background so that you can actually see these rare events. And so we'll talk about what are the kinds of sort of false positives that you can get and how you can overcome that. And then I'll show you the actual experiments of how we're doing that. And we sort of we've done a nominal sort of very localized dark matter search with that, just as a sort of demonstration. So dark matter, just to give a very broad overview. So to the best of our knowledge, all of the normal stuff in this yellow bar is only a small percentage of the sort of, I guess, gravitational matter in the universe. So there's this dark energy stuff, which makes is responsible for the accelerating universe. But there's also this dark matter, which again, we don't know if it exists, and we have no idea what form it is, but there's a lot of evidence that something like that should exist. The first evidence, I think, was in the rotation curves of galaxy. So things are spinning faster than you would expect for the amount of normal matter that you see. And so one plausible explanation is that there's this extra. Let's see, do I have that? Oops, let me just let me get a pointer here. Is that there's extra matter that we can't see. So that's sort of maybe the first first evidence. Also, if you look at kind of structural kinds of things in the CMB or in these sort of globular clusters, you find that it's hard to imagine where some of the large-scale structure in the universe comes from. And a plausible, candidate for seeding the structure is dark matter. So that's another place. Also, in certain gravitational lensing experiments, one can sort of see that there's lensing from stuff that isn't the things that you actually see. So all of these things sort of say that there should be something out there, and there's a lot of different explanations, everywhere from just sort of some heavy particle that's stable to black holes, to the type of dark matter that we'll talk about, which is sometimes called light dark matter. And so in particular, there's these two candidates. One is called the axion, and one is called the hidden photon. Again, I don't want to talk too much about their high energy properties, but they have a few kind of important characteristics. So one, the axion actually was thought of a long time ago as also a solution to the CP problem. Basically, one would expect the neutron dipole moment to be larger than it is, and in order to not have some fine tuning, one way of doing it is to introduce a new dynamical degree of freedom, which then results in these particles. Again, there's different flavors of it, but at least one flavor of it, or I guess there's two different flavors that would be reasonable candidates for dark matter. And these are supposed to be pretty light, like somewhere, like less than an electron volt. So, most of the particles that, you hear about for dark matter experiments are pretty heavy particles, and when they come in, they sort of will knock a nucleus around and do a big effect. These are sort of overall go by the name of WIMPs. These are sort of they have mass, but they're very light. So it could be an electron volt, but it could be even 15 orders of magnitude less than that. So we don't really know, and that's sort of the difficulty in the search space. But one characteristic that these have is that they can convert from sort of axion-like matter into electromagnetic fields. In the axion case, this is mediated by a magnetic field. So if you have a strong magnetic field, that can kind of scale an interaction between the axion field and the electromagnetic field, and produce. So basically, when axions go through magnetic fields, they can sort of oscillate into photons. Hidden photons are a similar kind of thing. They have many similar characteristics. They basically, anytime there's an impedance mismatch, you can in principle get some conversion, although it's very small. And I don't know if these are motivated specifically to solve some other problem, but at least it's plausible that their existence is consistent with everything we know, and so it's at least something that could be there. And as we'll see, because they sort of have similar detection mechanisms, you can kind of search for them at the same time. So that's kind of what we're looking for. And
okay, quick question there. Can you distinguish between the two? If the detection mechanism is similar, can you?
Yeah, because basically, if it were,
or you'll say that
you need a magnetic field, so you can kind of use that as
the. Thank you.
Yep.
And what would make a photon hidden, or it's still
it's not real. I mean, a hidden photon is just a name. I mean, it's some other scalar field that does have mass. But there's just a coupling to the electromagnetic field. And I mean, again, I definitely do not claim to be an expert in this. I mean, the way it's been explained to me, it's not something that so much should be there. It's just something that you can write down, and then it's kind of consistent with everything else. You could say, well, imagine the dark matter was a scalar field, and then it could. It could have this mass range and still satisfy all of the kind of astronomical constraints and all of the precision measurements that we've done, and I think also because it's a little bit
the axion, because it's trying to solve some other problems, the models for it actually give some bounds on sort of how strongly it might couple. So one nice thing is that if you look for it in a place, you can very likely exclude it. At least, I mean, like with all of these models, you can make them more complicated and then kind of have fine tunings. But at least for the one, there's sort of a couple of theories, and they sort of put reasonably tight bounds on it that we can actually reach in these searches. And if you so the hard part is sort of this 15 orders of magnitude in mass, right? So if you look at a place and you don't see it, it's probably not there. But it's hard. You have to search with a fine-tooth comb in some sense. And then with the hidden photons, again, I think because it's there's less other things that they're trying to do with it, there's less constraints. I suppose if you remove those constraints from the axion, you may also be able to have a wider bounds as well.
Excuse me, just a quick question. Is this hidden photon, I suppose, then is a vector particle, right? Spin 1, contrary to the axion. Is that the main difference?
I'm actually, honestly, I'm not sure. I'd have to check. I apologize. I don't want to say things I don't know. I would say I've sort of been brought in as almost maybe not quite a technician, but I sort of come into the picture more once it gets turned into a microwave photon. So yes, I've understood a little bit about these couplings in terms of how they how one should design things to couple. But I'm still fairly impoverished.
Sorry, I just say that because, of course, in the case, the hidden photon is just through the dielectric constant, right?
Yeah.
So a spin should be conserved somehow. So I should have the same spin as the photon. Whereas the axion, because you need a magnetic field, you may convert a spin 0 to a spin 1. That's just the reason my reasoning here. But
that makes good sense. Yeah.
Okay.
No, thank you.
All right, thank you.
Yeah. Okay. Okay, yeah, and so we kind of come in basically on so you want to convert it into a microwave photon, but then there's the question of how do you measure that microwave photon once it's there, and that's sort of where I got involved. So the basic the basic mechanism again is so it will convert either through the magnetic field or through the dielectric, and there's a sort of the expected, if you just have so what we do is we just take a box like it could be literally a copper box like this, and we seal it up and we try to make it as dark as possible, and then we look for microwave photons to appear. That's sort of that's the basic experiment. It's called a haloscope experiment. We basically just have a box that's completely sealed, and you look for photons to spontaneously appear. And sort of the ambient level of photons would be somewhere in the 10 to the minus 8 to 10 to the minus 5 range for axions. And I think that's probably assuming like a 14 Tesla field or something like that. And it would be sort of, the bounds are weaker for the hidden photons. They're, less than 10 to the minus 1, but could be much lower potentially. And so basically, if you make a box, and for the axion you have to put that box in a strong magnetic field. In the hidden photon case, you don't have to do that. Then you hopefully get a microwave photon in that box if the axion happens to be resonant with it, and then it will come out this cable. But or it'll be in the box. So the question is, how do you detect that photon? And so the way that it's currently done in experiments like ADMX, for example, that are searching for it, they basically just use the simplest thing, which is an amplifier. So you just, if you have microwave signal, you can just treat it like radio wave and put an amplifier, and then amplify it and detect it. The problem is, even if you use a perfect amplifier, and they're now using these quantum limited amplifiers that are reach the Heisenberg sort of uncertainty limit. And what that is that if you think of the electromagnetic field as having like the X and P, for example, the then there should be uncertainty of h bar. And so you can represent that by sort of having a blob here. And what that basically means is that when you amplify, you are stuck adding one extra half photon of noise. And so at low frequencies, if h bar omega is much less than kt, this is not such a big deal because there's already a lot of noise and it's not a big deal. And that's so in the regime that people are currently searching with ADMX and other experiments, they're in that regime right now. But as you go to higher frequencies, at several gigahertz, in a Dilfridge, there is no noise. So and so you're actually dominated by this sort of extra photon from the standard quantum limit. And so the question is, can you get around this? And the basic trick there is that instead of, if you can measure only the amplitude and have no information about the phase, then your uncertainty could look like this. So you'd have infinite uncertainty in the phase, and no uncertainty in the amplitude, ideally. And so this says that you should do photon counting rather than amplification as though it's a field. And so that's probably, if you kind of look at the numbers for trying to go past a few gigahertz in sort of frequency range for these axions or hidden photons, that seems like it's going to be a big win. And I'll show you, we actually do get a big practical win in doing it already. Okay, so that says we want to have a photon counter, and we'd like to build one for microwaves. So the for looking for like neutrinos or other types of particles, right? What's you typically done is you use either photomultiplier tubes like are shown on the left, or we also you can make superconducting nanowire detectors, or other types of photodetectors that are sensitive to a single photon, and so that's great. But until kind of people started studying quantum information and qubits, there actually was no single photon detector for microwaves. And so there's a couple of ways that one can do it. So the way that we're going to do it is sort of, I think maybe the first way is basically we're going to use a qubit and the photon's effect on the qubit to do it. So that's what I'm going to talk about. We first sort of saw this kind of effect, a little over 10 years ago. There's other methods too, with just even with superconducting qubits. There's you can basically, this one also uses a qubit, and you essentially have instead of having a photon in a cavity, you have a photon that just comes in on a transmission line and bounces off of a qubit. Actually, it's kind of a funny story, with this type of detector. Maybe I'll tell you in a second. But so there's anyway, you have so you can have this style. You can also make sort of an analogy to a photomultiplier tube by having a sort of a Josephson junction that's tilted, and when a photon comes in, it kind of switches the direction of a current, and so it's kind of a latching detector. And you can also, Alexandre actually proposed a really quite elegant mechanism that makes a sort of a Kerr metamaterial, and this is quite good. And I would say all of these have their advantages and disadvantages, but this one was sort of one that was sort of pretty straightforward given what we knew, so that's the one we've been pursuing. So this is kind of what it looks like. So this is kind of the cartoon. So we have a box where which is going to be sort of our transducer, where the dark matter can spontaneously appear. It's a high quality factor cavity. Then we have our qubit, which is sort of our detector of photons. But then we actually need to measure what the state of the qubit is. So we also have another cavity, which then acts as the detector of the qubit state. This is what it looks like. I'll explain this in a second. And just these are all of these happen at a few gigahertz frequency. So that's kind of the range that we're searching. I think this technique will probably go from maybe 3 gigahertz, potentially as high as, say, 30 gigahertz or so. So that's sort of the range that we could do. So we could probably do sort of 1 order of magnitude in sort of mass scale for this.
So, well, maybe that's a question that I can I'll ask at the end how you can go up to 30, but I'll let you continue.
I think just making everything smaller is essentially the answer to that question. I think after that, then other things start to break. But I think nothing breaks until 30. But it does get, some things get harder. Some things actually get easier. But it's interesting. I mean, I think actually, and Alexander's asking this because this is a very interesting question. I think from the quantum computing perspective, and I think that's one reason that I've been quite engaged in this research, because I think it's a nice example, especially with in the U.S. with these quantum initiatives and things like that. They're looking for examples where maybe high energy physics and quantum information physics really connect, and I think. This is one where it really is kind of natural, because we can sort of use these very kind of quantum information techniques in order to actually make a detector for this for the dark matter, but also the types of things that we look at in the dark matter are going to advance our kind of quantum information. For one thing in particular is that dark matter experiments are all about reducing the background, and that's really important for quantum information as well, and also just like studying what the backgrounds are. But it's often hard to motivate people to do it, and so I think actually we're learning a lot more. We're definitely pushing the bounds more than we are on those axes, more than we are in our quantum information experiments. Okay, so the Hamiltonian for this system is basically that you get. I'll explain this sort of term by term and what the elements are. There's basically a harmonic oscillator, which is our cavity, our storage cavity. There's a qubit, and then there's a coupling between them, which I'll explain in a moment. So first, let's talk about the cavity and this sort of funny geometry. So the cavity we're currently using is just this an aluminum box. I should say that right now we're doing everything with the superconductors, which is not so great for doing the axions, and we have a separate project to sort of try to make high quality cavities that don't use superconductors, so that we can put them in a 14 Tesla field. And that's a fun other problem. But for now, we've been using superconducting cavities, so we can sort of still do the hidden photon stuff. And the physics from the sort of once it gets converted to a microwave photon is all pretty similar. So this is, and so we kind of have this funny technique for making it where we sort of we want to make a box inside of a solid block of material, and we don't want to just cut it in half and make a box, because then you might worry about stuff leaking out of the seams or leaking into the seams. So what we do is we actually drill it from both sides, and you can think of it as almost a little bit like the mesh on your microwave, except that it's a little bit deeper, because we want very, very, very little power to leak in or out. And so basically you can just think of this conceptually as just being a box, but it's sort of a box that's made out of a single piece of 99.9999% pure aluminum. So it's just a kind of a technique for making a very a box that has a high Q. So we can get Qs of about almost 100. Well, our best Qs are maybe like 100 million or so. I think this one may have been like 60. And then the other piece is the qubit. So we make this is what's called a superconducting transmon qubit. That's a fancy name, but it's actually a very simple circuit. So it's physically what it is it's like a Josephson junction with an antenna. So this is the Josephson junction. The Josephson junction is just two pieces of aluminum where you see there's one wire, and then there's another wire on top, and in between the different steps of evaporation, we grow a very thin oxide layer as a tunnel barrier. So it's a sort of a tunnel junction, and basically these big pads act like a C, and the junction acts like an L. So it's like an LC circuit, which would be a parabola, but the Josephson junction is a very nonlinear inductor, and so it's instead of a parabola, it's actually a cosine. But we operate in a regime in which it's almost parabolic, but there's just a little bit of tilt here. And so if you go from G to E, that has a slightly different frequency than from E to F, and that allows us to operate just with G and E by just sort of using the right frequency. And so we can use this as a qubit, and so we can sort of approximate it like this. There are some corrections when you're actually doing the calculations, but this is conceptually accurate. And then there's the coupling between them. And so again, this is sort of a little junction with an antenna, basically. So you can think of it as just having some dipole moment. And the interaction is just the dipole moment times the electric field in the cavity. And so that looks like, you know, some coupling strength times essentially the dipole moment of the qubit, which, you know, we can just write as sigma plus plus sigma minus, and then times A plus A dagger, which is sort of the field strength of the cavity. And this is just sort of, you know, sort of all the dimensionful couplings there. And that's fine, but if the qubit and the cavity are at different frequencies, so what this basically says, if you sort of multiply it out, is that you can take a photon out of the qubit and put it into the cavity, or you can take a photon out of the cavity and put it into the qubit. But if you're off resonant, those terms are off resonant. So basically, you have to go to the next order in perturbation theory. You square it, and then you basically get something that looks like, you know, something like x squared, you know, of the qubit times x squared of this, or A dagger A of the qubit times sigma z. And I'll show you what that looks like in a minute. But basically, what that says is that the qubit frequency depends on the photon number in the cavity, this coupling constant you can calculate from sort of the parameters of the qubit. So that's sort of the interaction. This is basically the simplest interaction you can have. It's just what you get from putting the qubit in the cavity. And so we have to, in order for any of this to work, we have to get very cold. So this is a dilution refrigerator, but in this case, it's not a quantum computer. It's a, you know, because it's a dark matter searching thing, I guess, or something. But you know, so we go 4 Kelvin, which is, you know, kind of cold. This is cosmic microwave background temperature, right? This is, you know, much colder than space, and this is, you know, 100th of a degree above absolute zero. And, you know, we have lots of microwave cables for sending stuff down, and then we have, you know, filters and, you know, all kinds of different things to just basically keep all of the room temperature and higher temperature radiation from getting inside here. We have magnetic shielding and thermal shielding and things like that. And so, we want to try to get both the electrons and the phonons cold, but also the photons. That's really important. Okay, so this is I said we had a qubit, we have a cavity, and then if we take that interaction term and there was a sigma z there, and we kind of group it, you can kind of see that what it looks like is that the qubit frequency has now a dependence on A dagger A, which is the photon number. And so if we measure the qubit frequency by doing spectroscopy on it, so this frequency axis is, you know, we try to excite the qubit at its resonance frequency, and if there's no photons there, it goes here. But if we put a little bit of if we put like a coherent state, and if we drive the cavity a little bit, then there will actually be there's some probability there's a photon. And then what you see is that the qubit frequency is at a totally different frequency. And you can see, by the way, this is a little bit like a Stern-Gerlach experiment, right? It's sort of, it really is for the field. It's really showing the essence of that the electromagnetic field is quantized, right? Because you don't ever get anything in between. You can't ever get half a photon. It's either 0 photons or 1 photons or 2 photons. And it's separated by this energy scale, which we call 2 chi. So that's kind of a spectroscopic version that says that the qubit is detecting these. And in principle, one could just repeat this experiment, and what you would see is a very big peak with 0, and then you'd see a much smaller peak with 1, and you could take the ratio and try to figure out how many photons are in the cavity that way. That doesn't work. So that's not a very good. It's hard to do that really accurately, and so we do a slightly different version of it. The other, you know, we first saw this actually when I was a graduate student back at Yale, you know, and actually, you know, when I showed this data to my advisor, Rob Shulkoff, I asked him actually, because he was you know, actually a lot of people in our field were former radio astronomers, you know, and Rob was as well, and I said, hey, you know, this is like a photon counting microwave detector. Like, would this be good for, you know, like radio telescopes or something like that? You know, could we use this as a detector? And he said, you know, Dave, I mean, it's true that it's very sensitive, but I mean, it would be a terrible detector. Like, the only way it would ever be a good detector is if, like, you know, these microwave photons spontaneously appeared in your microwave cavity. And I mean, that's just not, you know, not going to happen, right? And so this is actually like, and so I was like, okay, you know, you're probably right, and he of course was right. But then, you know, sort of a decade later, then Aaron approached me and said, so we have this problem where these microwave photons spontaneously appear in a cavity, but we don't know how to count them, and so. It turned out that it was useful. So the question is, how do we convert this physics into something we can see? So we're going to do a slightly different type of experiment, which is called a Ramsey experiment. And so the idea is that we start out with our qubit. This is if there's 0 photons in the cavity, and this is if there's 1 photon in the cavity. And in both cases, we're going to start out with our qubit just in its ground state. And then we're going to do a pi/2 pulse, because it's rotating it by pi/2 in the Bloch sphere. So this is ground, this is excited state, and this is like 0 plus 1 or G plus E. And so we do this, and so if we arrange this pi/2 pulse to be exactly at the n = 0 state, then you know, nothing will happen, basically. But if or actually, well, all right, it's not quite right. So if we want this pi/2 pulse actually to hit all states, so we want a very broad pulse, but we want the if we're rotating in a frame which is going at the qubit at the n = 0 state, then in that frame nothing is happening. But since the n = 1, the qubit has a slightly different frequency, so in that frame it's actually precessing. And so if we wait for it to precess, you know, by pi, then when we flip it, we can actually instead of going to down, it's actually going to go to up. So basically, we're going. I don't know if you can see me, but you know, we sort of go. We start down, we go up. If it's in the excited state, it will rotate and then come up to the excited state. And so what we're able to then see if there's a photon there. Actually, I should say this is really not measuring actually whether it's 0 or 1. It's really measuring whether it's even or odd. In the way that we're doing this, but since it's mostly going to be 0 and just a tiny bit 1, that's equivalent. So that's great. But what's really special, I think, and unique about these sorts of measurements that's different from any kind of conventional photomultiplier tube or even our eye, right? So when we detect a photon with our eye, the first thing that happens is that photon gets absorbed, right? It gets destroyed and turned into an electron, basically, right? And so, you know, in some sense, with optics, we essentially never measure a photon. We measure a photon that once was, because the first thing we do always is we destroy the photon. But in these experiments, no photons are harmed, and it's a very ethical experiment. So we have and that's because you know, we're only manipulating this qubit, and the qubit isn't absorbing it. It's just being shifted a little bit by it. It's sort of, you can think of it as changing its spring constant or something like that. And so it doesn't actually, and that's really important for these experiments. So what we've done is we prepared you know, we just wait and let the cavity go to its ground state, and then we do this experiment a bunch of times. And what you see is that most of the time it just doesn't get excited. Every once in a while it does get excited, and then and then if we intentionally put 1 photon in there, then it gets excited almost every time, except for a few times it doesn't get excited. And I want to emphasize that, like in this n = 1 case, we're like, this isn't each point is not like a new experiment with a new photon. It's the same photon in the storage cavity, and we just are doing this protocol over and over again. So the qubit is sort of new each time, but the cavity the photon stays in that cavity, and that's quite important. And so I mean, and you can see that in some sense you can tell that this is 0 and this is 1, even though there's a few like false positives or false negatives. And the thing is, you know, a false negative is bad because it means that there was, you know, dark matter or hopefully, but more likely a background photon that was there and we missed it. And so that sort of slows down our efficiency. So every time there is a photon and we miss it, we have to do the experiment again, essentially. We have to, you know, we have to wait again. But this is even worse because every time we measure a false positive, we think we have dark matter or a background photon, and then we, you know, would go back and measure much more carefully, right? So, and you see, we do these measurements very often. So each one of these measurements takes maybe 2 microseconds or something like that. So we're measuring every 2 microseconds, and you know, if we're lucky and the dark matter is reasonably strong, it might, you know, we might get a count every second or so. But if every microsecond we're measuring, then, you know, that means we better have part per, you know, we can't have a dark count of, you know, if we only did one measurement, we would be right most of the time, but the times that we were wrong, every time we're wrong, we basically have to wait another second. And so that's really bad. And so what we need to do is be able to figure out a way of dealing with these false positives, ideally also the false negatives, but these are less bad because this just slows us down by a few percent. This actually makes us, you know, slows us down by the ratio of the sort of the rate of dark matter to the rate of false positives. So that's really bad. Okay, and so now what we want to do is come up with a way of doing that, and the basic idea is to use the fact that this is a QND measurement, so that we can measure the same photon many times, and then if we have error in our qubit readout, we can sort of check to see, you know, when we take, you know, many, you know, n measurements. We can check to see that they're basically, which is it most consistent with? Is it most consistent with having no photons in the cavity, or is it most consistent with having one photon in the cavity? And we can use the information from all of them. So if there's, you know, one false positive, we can reject that. If there's a false negative, we can assume that there's probably still something there. And so the way to do this, and this was come up with or suggested by Konrad Lehnert, is to use essentially like a hidden Markov model for doing this. And the basic idea is that you have your actual observations, which is, you know, whether you think the qubit is excited or ground, and you may be, you know, you're mostly right, maybe, but not always right about that. And then you have these sort of hidden states, which are basically what the qubit actually is at that time step and what the cavity actually is at that time step. And the goal is basically to figure out, to infer what this N0 was, whether the cavity had 0 or 1 photons at the initial time based on all of this observed data. And so, you know, and I guess this is also where I put all the kind of statistics here. So our qubit lasts for, you know, 100 microseconds. The cavity lasts for about half a millisecond, and there's about 5% of qubit spurious population. So even if your measurement is perfect, you're still going to be wrong, you know, one out of 20 times. You'll measure an excited state qubit when you shouldn't. And we can do an experiment every sort of 10 microseconds or so, and then the dephasing is sort of a little bit relevant for some of the things there, but and then yeah.
Quick question. So the 5%. So this is after reset. So you're doing some kind of active reset.
So we're actually. Further, or? I mean, this is just. This is not so. Actually, I can sort of show you how we get around that in some sense. But the this is just if you leave it there. If you just aren't doing anything to it. As a practical matter, I'll show you in a second. We actually don't have to reset it because. You know, when you do it this way, there's nothing that says you have to start in the ground state. You can actually do this same protocol and start in the excited state, as long as you know where you were, what you really care is, did you flip or did you not flip?
Okay.
Yeah. And so, you know, basically you do some math. Basically, again, all this is saying is that you're taking all of the information you've got, which are these you know, these R's, and then you're essentially backing that out to what the probability of having a photon was originally. And, you know, but you can see there's a couple of different things that could happen, right? So you could have a photon at each of these steps. You could have a photon in the cavity, and then you measure that the qubit flips, and then you measure that accurately with when you read out the qubit. So that's like what you'd ideally like to happen, and maybe that happens. I mean, I think the best we've gotten this, you know, is that this happens 90% of the time or so. But you know, but another thing that could happen is your protocol could be slightly messed up, like due to dephasing or some other thing, and then you could have nothing in the cavity, but the qubit gets excited, and then you measure the qubit accurately and it flips. Or you could have that, you know, the cavity has no photon, the qubit doesn't flip, but when you measure it, you just measure it wrong, right? So you know, so both of these are bad. This one's good, but again, you know, you can't tolerate this 10% of the time. But the point is that if we kind of if we measure it like 30 times, then we can use this, you know, we can basically say which one is most likely. And so what this looks like is something like this. So we do, so each one of these dots is us doing a parity measurement. And so if it's in the ground state, basically the probability of it getting excited should just always be 0. And the probability of it being 1 should be 1. And so we do these parity measurements, and basically, you know, nothing should happen. So this is the ideal case, like if nothing were to go wrong. This isn't data. And then if we were to do if there were and then so this is like what you should observe. This is then what this is what the probabilities that you would actually infer. So these are the measurements of the transmon. This is the inferred measurement of the cavity. So what you start with, and you don't know what it is, so it could be 1 or 0. They're both at a half basically. But each time you measure no flip, you become more and more confident that it was in the ground, that there was no photon there, and that the probability of having 1 photon there is very, very low. So that's kind of how that works ideally. If instead there was a photon, what you expect is that after each measurement, the qubit should flip. So it should go from ground to excited to ground to excited to ground to excited. And this maybe gets at Alexandre's question, which is that so we actually don't have to reset in between. We just keep doing the same protocol, and we just look that it's flipped from the last time. And that's the signal. And you can see here there's actually there is an error in this trace, right? That this one, it didn't flip that time. And again, and it looks like in this case, I guess that it really didn't flip because or that the qubit or the qubit decayed during the readout or something like that, because it didn't maintain the thing. So, but still, we can be pretty confident that this is a real photon, and so you can let's see. So the probability of it of 1 started out at close to 50%, but then it basically gets steady, and the probability that it could have been 0 goes down and down and down, and then you see when there was this little glitch, it went up a little bit, but then it continues to go down. So we can say that this does represent a real event. and the other thing to check here is that if you look at the axis here, it's exponential in the number of measurements you do. So this isn't totally for free, right? If we do 30 parity measurements, it takes 30 times as long to do the experiment, to measure it. And so if the photon decays in some time, then that can hurt us, and it could potentially just take us longer. So it can affect the duty cycle, although the measurement is still pretty fast compared to the lifetime of the cavity or the lifetime of the axion. So it's not that bad in terms of duty cycle, as we'll see. But for each measurement we add, we can really start to lower it. And you can kind of pick your threshold. So if you want 10 to the minus 14, you can do 25 measurements. If 10 to the minus 7 is good enough, then you can do 12 measurements or something like that. But it's a very good trade-off. So you do a few more measurements and you get much better suppression. And that's really kind of the key thing to make this work. Okay, so now we have our kind of idea. So now let's actually see what it looks like. So this is our qubit, and we can do some spectroscopy. So this is different levels of drive. So we intentionally drive the cavity with photons, and so with a coherent state with an amplitude of 10 to the minus 3 up to a couple. And so you see when you're driving here, it's mostly mostly 0, although there is some stuff even at pretty low drives. You can still see a little bit of a 1 photon peak, and then you can see many photons when you go up higher. Okay, and so again, we can extract the number of distribution if we want. And one thing that this lets us do is calibrate our drive, right? So we can sort of do an absolute calibration of the drive by using this qubit. So that lets us sort of calibrate the photon number that we're driving with. And then what we do is we start driving at a signal which is easy to see, a little bit less than 1 photon. And then we keep dropping our drive, and that's what each of these points are. And then we try to measure it using this technique. And so this is basically the probability that there's 1 photon, or the n bar, basically. And so this would be the standard quantum limit. So this is like a half, right? So, and so if it's a large signal, it's very easy to see, and it continues to go down, and then at some point it saturates, it stops going down. So we're now driving. So now we're not, out here we're not detecting what we put in. We're detecting something else that's there. So either it's some kind of a false positive, at least with respect to our drive. So it's either that we're having false positives from our detection scheme, like that there were no photons and we think that there is a photon there, or that there's background photons that are actually there that we're detecting and they're real, but we didn't put them there, and which is what we think is the case. And so you can actually tune this. You can tune your detector kind of threshold, as I was saying, by kind of how many measurements you do. And so that's this kind of lambda threshold. So we chose that to be 10 to the 5 because essentially we were getting to a few times 10 to the minus 4, so we wanted it an order of magnitude less than that. So this is what I was saying about sort of trying to, you can sort of adjust this threshold based on what you're seeing to sort of, kind of make sure you're not having any positives that are due to the detection scheme, but maintaining your efficiency. So we're actually measuring for about 40% of the time. So it's it's pretty good that way. And so so this is kind of we can actually look at events. It's almost like a like a real detector experiment or something like this. And so so you can histogram them. And so at 10 to the minus 2 or almost 10 to the minus 1, you can see there's a lot of events that are above this threshold. And if we go down to essentially no drive, you can see that there's just a very small number, like 4 events or something like that here, that actually get past the threshold. And so and again, we believe that these are just residual, likely to be residual thermal photons. So a question is, how much faster is this than if you were to just use an amplifier? So the way to think about that is that if you have some source rate of photons that you're coming in, and then there's a background rate, if the background rate is higher than the source rate, then there's basically you need to make the source rate higher than the shot noise of your background. So that's like the square root of the number, and so you can solve for the amount of time that it would take to do that. And basically, it's proportional to your background rate. So you just want to lower that background rate as much as you can. And in our case, this was our background rate compared to 1. So you just invert that, you get something like a factor of 1,000 faster. So this is I think going to be really critical. You know, I didn't go into a lot of detail, but you know, I should say that as you go to higher frequencies, the signal rate also tends to go down. So it's not just that we'll sort of go faster than before, but we'll sort of need to go faster because we'll have less signal this is actually going down with frequency. So it's important to make this also go down with frequency if you want to still be able to measure stuff. And so then, what we've done next is we've actually kind of done, you know, kind of essentially a hidden photon search, but just at this one very particular frequency. But this sort of let us go through all of the, you know, the stuff that you need to do in order to understand the systematics and the backgrounds and things like that. So again, so what we do is we need to wait for the dark matter to build up in the cavity. So we wait for basically one cavity lifetime. Then we do a bunch of repeated measurements like we did before, and so, you know, in this case we did, you know, something like 15,000 experiments, which took about 15 seconds, and then so the integration time, which is sort of the time spent, you know, collecting photons here, is about 8 seconds. So the you know, so basically the ratio of these is the duty cycle, so 65% or so, and then we measured 9 photons in that time. And you might say, like, why did we go for 10 seconds and not an hour or a day or a week or something? And I think so, you know, again, so the thinking is that around this amount of time, actually, if there was a dark matter photon, if there were axions or hidden photons at this frequency, you would expect to see some counts for this amount of integration time. And what you have to do is, this is only sensitive basically at this frequency, not at this line width actually, but at the line width of the axion, which is constrained from, like, there's some cosmological constraints about basically how fast it can be moving. Basically, the width of the axion comes from Doppler broadening, and that comes from how fast it could be moving. And if it were moving too fast, it would escape, you know, the galaxy. And so that puts a limit of like part per million or so. So roughly speaking, we think that, you know, each measurement covers 1 part per million of the spectrum. And so we need to then sort of sweep through this. You know, so to get 1 octave, we need to do 1 million measurements. And so so the idea is that we want to be able to, so you don't want to make this longer than you need it to be. And this is sort of about the right amount of time, give or take. Yeah, so again, what we want to do is, you know, the sort of the nominal thing we're sensitive to is just 0 or 1 photon in the cavity. Actually, it turns out you can also see off-resonant photons from the cavity as long as they're, if the signal is much larger. So it's much less sensitive to those photons, but there is still some sensitivity, and you only get to measure the odd numbers rather than the even numbers. But, you know, but since it's random, you would expect, and it's a large signal, you would expect there still to be some signal there. And so basically the kind of the story I told you mostly refers to this very narrow line that goes down there, but there's actually there's sensitivity in this whole region here that's shaded, so there's a little bit, one has to be a little bit more careful. And so now this is like kind of the standard plot that people make with for searching for axions. So this is the ADMX experiment searching for axions, and I think the more sort of the easier to detect theory for axions lies right along this line. I think the harder to detect ones is maybe down here. So if this were axions, we would be able to exclude both theories. For hidden photons, I think the reason that those bars aren't on here is because this, in some sense, we're doing a hidden photon search. So those theories don't apply. But anyway, what you can see is that you know, this is actually quite, you know, this is the most sensitive measurement of something there, and it's in a reasonable amount of time. It's not like we just integrated on one spot for forever. And so then you know, the next thing to do would be to then, like, you know, try to scan this through you know, at least an octave. And so ADMX has been going through, I think it's like an octave every year or two or something like that, and I think or a couple of years. I think it's it was like 2 or 3 years per octave or something like this. And I did some quick calculations. I mean, don't hold me to it, but I think with at least for hidden photons at this level, I think if we were to scale this, it seems like we could probably do it in, like actually a few cooldowns with if we did a couple samples at once. So maybe a month or two in principle. In practice, it'll probably take us a year to get to that point, but it's a reasonable scan rate, at least as far as these things go. So what do we have to do next? Well, I guess there's this picture, which is like, so one challenge for axions is we need to like we need to put it in a big magnetic field, and so we need to make a cavity that can take that have a high Q in the big magnetic field, like at least 1 billion, and then we also, once we get that photon, the photon will be here. It won't be next to the qubit. So we need to then somehow get it from here to there. And so I think we have basic ideas about how to do that. It's very similar again to things that we've been doing for quantum information and quantum networking and things like that. So we're getting pretty good about moving photons between cavities via cables, even single photons. So I think we can do it without too much loss, but it's a more complicated experiment. So the big question really is, like, we saw that there's still more than 10 to the minus 4 photons in the line. We'd really like to get the background, below 10 to the minus 5 or 10 to the minus 6, and so this is also relevant for quantum computing as well, because the probability of having a background photon in your cavity is also basically the probability of having an error if you're using that as a memory. And so if that's above 10 to the minus 4, for example, that's, at least for some codes, that's already would stop you from doing error correction and things like that. So it's quite relevant for quantum computing as well. And so we're trying to understand this better. Is it, is it like one possibility is just our line the photon, that the lines are, we're still not thermalizing the photons or the electrons well enough, and that it's just sort of some stray light essentially that's coming in. Another possibility is that there've been is that if the qubit is hot, the qubit actually, the wave function of the qubit and the storage cavity actually are overlapping. So the qubit is actually a little bit cavity and the cavity is a little bit qubit. And so if something were to, so the same processes that cause relaxation in the qubit could also potentially cause heating in the cavity. So if there's qubit heating, I should say, that could do it. So if there's quasi-particles, or there's been some measurements of like just like cosmic rays or just ambient radiation from the metals and things like that nearby, if any of those are causing the qubit to be heated, and we see that it is heated a little bit at least, that could sort of end up heating the cavity. And the rates are, I would say both rates are are like not inconsistent. I think I wouldn't be surprised if it was either one. So we're trying to understand that better, and we can try and use we could do things to try to make the cross section of this less for cosmic rays would be one option, or do some shielding or something like that. The Fermilab guys that we're talking about are very excited to try to put these experiments in mines. They have the mines, so they want to put something in it. So that they're interested in doing experiments there. But I don't actually think that's necessary. I think if we design, if we determine that to be the problem, I think with design we can still improve this quite a bit, and we can also use different materials and things like that. So that's the other thing. Another thing that could be interesting is could we do even better? Like, so this is quantum in a certain sense. It feels quantum because we're manipulating single photons and using qubits, and we are doing very quantum experiments, right? These Q&D measurements and things like that. But if you look at it in a black box, like if you're a dark matter person and you're not a qubit person, then what you see is that they made basically we made a photomultiplier tube, right? It's a fancy photomultiplier tube functionally, and that feels like a pretty classical device, and I certainly wouldn't argue with that. But there's another thing we could do, which is we could try to enhance the coupling of the dark matter to the photon field by stimulated emission. So one way you can think about it is that the dark matter field is basically is like an oscillator or a driven oscillator, and then the cavity is a driven oscillator, or is an oscillator. If and the amplitude, the energy in the dark matter field is sloshing over like coupled oscillators. But if you already have photons in the in our storage cavity or our transducer cavity, you actually enhance that by stimulated emission. You get like a factor of, for a weak process, you actually get a factor of n, just like a laser, basically. And so if we were to prepare the thing is we want to see exactly one photon, and we want to have no background. So we don't want to put a coherent state in there because that would cause a big background. But if we could put a Fock state in there, if we could put exactly, say, 8 photons in there, then you would enhance the rate by. Then what would happen is the dark matter could basically change you from 8 to 7 or 8 to 9. So for example, if we looked at the probability of getting 9 photons when we put 8 photons in there, then that rate is actually going to be going up by a factor of 8, basically. And so we could, in principle, like, not just improve the, so before we were sort of trying to improve the background rate, lower the background, but we could also potentially enhance the signal. And so we're actually able to make Fock states in the lab in these cavities. So I think we've done that up to like 4 or 5 currently. And that's probably actually the best bang for your buck, is around 4 or so. You already get a noticeable win, and it's not too hard. When I should mention that these states do decay faster, so your integration time goes down. So what you're effectively doing is, if you can make, where this really pays is if you can make a better cavity. So if you can have a cavity Q that's much better than the line width of the axion, then you can then you're sort of not as efficiently using that quality factor as you would like. And so this allows you to kind of match the quality factor of the cavity in some sense, the lifetime of these photon states to the axion line width. And so it's sort of a better impedance matching in some sense. Yeah, so this is another thing we're looking into, and we've done it. I would say we've made the states, we've done the experiment. Thus far, I wouldn't say we've definitively seen that it actually improves things once you include all of the, all of the errors in making the states and things like that. But it's a fun. There'd be a fun way of really having a quantum enhancement of the signal. And yeah, I guess I already explained this part. But so we also really want to search for the axion, not just hidden photons. So with that, I'll conclude. So I think we sort of used kind of qubits and quantum information techniques to help with dark matter searches. I think it's a real speed up. I think this is I think it's actually pretty likely that this will go into the next the next generation of the ADMX search from, say, in the 3 to 30 gigahertz range. It's already, at least at one point, kind of excluded a point of hidden photon dark matter. If you're interested, you can look at the paper. It was published pretty recently. Yeah, so it's been fun. I'm happy to take any questions.
Right. Thank you, Dave. Thank you for the great talk. I'm sure there are questions. So you can either raise your hand or just go ahead and unmute yourself.
I have questions. So the first question is about what's slide 3.
Oh.
You're saying that
the sound is not perfect on your side, Camille.
somebody asked a question, I'll connect.
Okay, I think there was a sound issue there. Another question while Camille solves this? Yeah, David?
I have one. Okay. You mentioned gap engineering for your cavity, right?
For the qubit.
So for the qubit, okay, right, yes, sorry. Yeah. But I was also wondering about the cavity itself. I mean, it's a very naive question from someone who doesn't, it's not my field at all, but I mean, your cavity, you drilled all these holes, right?
Yes.
And so you're saying that these holes basically are too small to make I mean, photons can leak in, can't leak in.
Yeah, I mean, I should say it's not. We do then cover them with more metal. So.
All right. Okay. So that's something.
But actually, you know, the microwave photons can't get in. The reason we cover them with metal and we put it in a magnetically shielded box that's inside of another magnetically shielded box that's inside of another copper thing is because we don't want infrared photons. So, you know, you know, there's you know, even the next stage up is at like 100 millikelvin or even close, you know, 700 millikelvin, and so at that level you can get sort of things that like above the gap of the aluminum, for example, and that can create quasi-particles. And we've seen, actually we had a, you know, I don't think I have the slide with me, but you know, we spent actually, one of the big things to get this to work was and other stuff that we were doing is that we were having this big problem that whenever we would put our qubits in these sorts of cavities, that they would just be terrible, you know, like 10 times worse than what you saw here, and it was basically just, and it's not that we hadn't been doing it, but like we hadn't been sealing things enough, and just radiation from outside was coming in and just, you know, and heating them and making them worse. And so so we've actually gotten pretty paranoid about this. Because we spent a lot of time iterating to do this. But yeah, so we have it. Yeah, so I think, yeah, there's that cavity, and then there's sort of a copper. Everything is kind of covered in copper, both to seal it, but also to thermalize it. So the microwave photons can't get out or in, but if we didn't do that, you know, IR photons could potentially get in, and also, you know, I guess it probably doesn't do very much against radiation, but maybe some sorts. And then we put it in magnetic shields, and then, you know, again in several layers of radiation shield as well.
Okay, that's good. Another question. So in the interaction between this hidden photon, right, and the real photon would be through some dielectric medium, right? And so what is that medium? Sorry.
Well, in this case, I think it's basically anytime you have like yeah, like, I mean, essentially like a, you know, discontinuity in the impedance of space. So I think it's basically the metal vacuum interface that gives you the thing here.
That would be the source of the transition.
Yeah, I mean, there's other schemes, like for higher frequencies, like people are trying to put like just like Bragg stacks basically, and then where you have alternating dielectric media, and that can affect a similar thing. And in fact, that's something that we'll also probably try to do. So, you know, when I mentioned that, you know, in order to do this, we need to make cavities. And if you make a copper cavity, the best you can do is maybe 50,000, maybe more like 20,000, something like that quality factor. Whereas the axis, which is both just a short time to do all these experiments, like you know, in terms of like how long it actually takes to do that parity measurement now, you know, if you have a Q of 1 million, you've got plenty of time to do it. If you have a Q of 20,000, it actually starts to be hard to do it in that time. Also, the axion line width is part per million, so now you're sort of you're not integrating as long as you would like. So we'd really like to have a quality factor of 1 million, and I think with copper you can't do it, or silver, and I think also superconductors just at 14 Tesla. So I should have mentioned maybe earlier that this coupling scales like b squared for the axion, and so if you're at like 10 Tesla, even like 10 Tesla versus 1 Tesla is a factor of 100 in signal, and that comes in squared in the thing. So it's sort of you win in some sense like the fourth power of the magnetic field. So I mean, I have thought about it, and I actually do think that it's worth more serious consideration about, like, if you could do this at 1 Tesla or 100 millitesla, you know, maybe you could make a much bigger magnet and then put more stuff in there. So there might be some trick, but it's hard because it scales so strongly with the magnetic field. Anyway, so what we're trying to do is to have a dielectric cavity, so that we might have essentially a few layers of dielectric that create a mode, and then have maybe a copper shield around that. That would be for axions, not for hidden photons. Although of course it would also work for that.
Okay. Thank you.
Yeah.
Yeah, I have a question. So what about the size of this accumulation cavity? So you said it's the coupling scales in magnetic field squared.
Yeah.
For the electric field, is it linear? So then if it's linear, then I guess it doesn't matter how big you make it, because if you increase your mode volume, you have less coupling, but you per unit volume. But yeah.
I think actually it scales like the volume, and I think it's because I think that part probably cancels out, but I think there's basically, and the way I think about it is just there's more essentially more space where the axions can interact with the magnetic field inside the cavity, but but yeah, the scaling is like it's b squared v basically.
Yeah, but I'm a bit confused. You said in your last part that by increasing by going to higher modes, you have more you have stimulated emission. So it seems to also that this suggests it also depends on the 0-point fluctuations of the field of the mode. And so then I would have thought if you would increase the volume, you would also increase the coupling per unit volume, but
yeah, I mean, I think, I guess well, it's in some sense, I guess it's a question of like, how big these particles, like, in some sense, I think well, let's see, so I mean, in terms of the spatial coherence over the field of the axions, it's very big. It's like football field size or something like this. So the axions themselves are so basically you can I think you can kind of think of the axions as basically just being like a constant field in some sense. So I think on the one hand, I guess if you were to shrink the cavity, the electric field in the cavity is stronger, but I think in the end, my understanding is that there's like a form factor thing that has to do with the geometry of the cavity, and that probably might suggest that having it be shorter is better slightly, but then there's also a volume term, so it might end up. Maybe it ends up being like cross section and not like volume once you include that or something like that. But it definitely, I think in general they want bigger cavities ideally, and that's in some sense the reason actually why it gets harder to detect these as you go to higher frequencies, because basically the volume of the cavity gets smaller, and that actually is a net loss, right? So you wouldn't, for example, want to do this on chip. Because it would be great if you could do it on chip, because then we could I could make 100 of these in a small package and multiplex the readout and then just and scan much faster.
Okay. And so the axion field, I have to think of it like a huge classical coherence state, not some thermal. Thermal
it's a huge classical coherence state, and there's lots of photons there's lots of axions in it. It's not like it's
so it's like a that they like condensed in a.
Well, I mean, I think it is like a thermal field, but I think it's just it's just that it's the spatial coherence is slowly varying. Yeah.
Okay. And so, do you have any plans for scanning the cavity frequency, or you would really just swap out the cavities?
No, I mean, because you only get 1 part per million per measurement, so you don't want to have to like warm up and cool down every a million times. So we're I think for the hidden photons, since it already kind of works well, and I still don't really understand like which of these is is more likely to be dark matter and like which all this stuff is sort of I mean, obviously the odds of finding anything are very small, even in the whole range that we'll look. So, but the for the hidden photons, since we can use the superconducting cavity and it already basically works at a sensitivity which is quite interesting, if we could just add tuning, then it would be good. And we've thought about different ways, and actually, I mean, there are experts here, so if you have any ideas, we're open to it. The simplest thing we thought of was that if we add essentially like a tunable qubit or a tunable resonator in the storage cavity, and then we kind of sweep it through resonance, it will shift the cavity and you can shift it by sort of order the coupling, so by order like 100 or 200 megahertz or something like that. And so if we could do that, then you basically, right? So let's say if we're trying to go from 4 to 8 gigahertz, right? So we would need and if we could scan 200 megahertz per cavity, right? Then we would need 5 cavities per gigahertz, and then let's say it's 4 gigahertz, so that's like 20 cavities. So we'd have to, and we could measure, we could probably actually, if we really wanted to, fit 20 cavities into our cryostat and just do it all at once, or we could in parallel, or we could do maybe like 4 or 5 at a time, and then scan it. And so yeah, basically what you have to do is, you say, well, you get I don't know, it's like 10 kilohertz or 100 kilohertz or something like this per 10-second iteration time, and then you do that for 100 megahertz, and then you can parallelize it as much as you like. So and I think some sense the expensive piece is actually the dill fridge, and you can actually fit probably quite a number of these cavities in one dill fridge, so if you wanted to. So I think that's sort of the plan for scanning, is that we would we just probably make like 4 or 5 at a time, and then just run these experiments in parallel with a tuning element. I mean, we also thought about tuning with like mechanical tuning, like by sticking a sapphire rod in, which is sort of the typical thing that other axion experiments have done, or actually also we thought about filling it with liquid helium, because we also have some experience with that, doing it for electrons on helium. But I think, for the hidden photons, just doing it this way seems like it might be the easiest. But if anyone had, the mechanical tuning is somewhat appealing. It just seems like that would be the conceptually simplest. But when we started to look at the technical details, it started to seem like it might actually be harder, at least for us. The thing is that we're really good at sticking superconducting devices in cavities. So for us, that's easy. Even if it sounds exotic, it would be better to do the mechanical ones probably could have a larger tuning range and things like that, and we are worried about affecting the quality factors and things like that too. But seems like it will work, at least for hidden photons. For axions, it's a different story. I think everything's harder with the big magnetic field.
Okay, thanks a lot.
So there's a question by Maxime, and we should also check if Camille's sound is back online.
I may have missed a detail, but I'm not sure I understand how higher Fock states in the cavity would increase the sensitivity.
Yeah. So basically, what you can think, right? The way you can think about the signal is that, so this is like the dark matter, and you're displacing it. You can just think of it as like applying this is like A plus A dagger or something like that. So you can think of applying A dagger to it. And so if the cavity is 0, right, you apply A dagger to it, and you'll just get something which is like of order 1, or order the scale of the dark matter field. That's the alpha, is sort of the amplitude of the dark matter field. And there's some prefactor here, which is of course very small. But the point is that since this thing is proportional to like A dagger, right, then you're going to get something which is you'll get a square root of n from when you apply that to the cavity field. So if the cavity field has photons in it, then you get an enhancement. That's
yeah. Okay, thank you.
Camille, did you?
Yes, I'm back. Do you hear me?
Yeah, no, it's good.
Okay. So I have a few questions actually. So one is related to the figure on page 33, where you're saying that you can exclude with 90% confidence that that the hidden photon doesn't exist for this range of energy and coupling, mixing angle.
Yeah.
So my question is more related, like, how does this compare to other detection techniques? Because usually when I think about detection of some elementary particles in particle physics, usually when we want to we need some really high confidence, I don't know, for example, when they detected the Higgs boson, they needed way higher confidence to prove that, to be kind of sure that the Higgs boson really existed. And okay, so here you're not, so here you're not saying that you found the particle, but the hidden photon, but at the inverse, you're showing that you didn't find it, so that it probably doesn't exist. So is 90% confidence enough, or how for example, for the other techniques like ADMX, what is their confidence? Is it also 90%, or is it more? I don't know. Was my question clear?
Yeah, it's clear. So yeah, I mean, yeah, I mean, I think this is right. It's just a mark on the the Gaussian or whatever. So I mean, if you go up, of course, we can be more confident that it's not up here than it is than it's not here. And so the confidence. So I mean, you just have to cut it off someplace. So I think that's just 90% was sort of chosen. But you could take the same data, and of course you could, if you wanted higher confidence, then basically what would end up happening is you would have a less exclusion there. I mean, one has to be careful about systematics and whatnot as well. But I think you can do that. And I believe this is on the same kind of. This is done in the same way as, say, this ADMX. So I think this is also the 90% confidence for the ADMX. And again, I think that's just sort of the standard. So I mean, yeah. So I mean, if you, of course, so you could say well, in order for me not to believe the theory, you might need to go even lower, so that higher up there's even more confidence. But I think yeah, this is just sort of just a measure of how. Of where we think that there's nothing there anymore. And obviously, as you say, that if we found if we thought that we had a real event, then we would have to do all kinds of other stuff to check. Right? We have to make check for. I mean, the biggest things are usually actually systematic things and not random noise things. But
right. Okay, thank you. And I have actually a second question. So I'm not totally sure it's clear to me, but this is more related to the paper than to the talk. It's so when you find this exclusion mixing angle, like you're saying that it's above some value, you're assuming that the density of dark matter is entirely made of hidden photons, right? So you're taking into account the full density of dark matter in space, right? And so I have two questions about that, because it's also comparing to other experiments, do the other experiments also take this hypothesis? And yeah, well, I don't know. Maybe if you have something to say about it.
Yeah, I mean, I think that's. I mean, it's obviously, it's not clear. We don't know what the dark matter is, or even, if it exists at all, really. So of course, how much you should use there. So I think that is a pretty typical assumption, is that they take that value and then they sort of throw into epsilon. I mean, you can of course if you had less dark matter, then you would just say that, if you said I want it to be 10% of what we think dark matter is, then that would just sort of renormalize this epsilon scale, right? But I think the typical thing that people do is they just assume that it's all of the dark matter, and then they go from there. But yeah, that's definitely an assumption, and it doesn't have to be correct.
Okay, because what I was most worried about is like, so in these kind of plots, actually I was never sure that everybody was taking the same assumptions, like the same hypothesis, and what was.
I mean, you know, I'm not 100% sure because I actually haven't gone through like say the ADMX plots and stuff like that. But the co-authors on the paper are part of ADMX, so they certainly know how those were done, and I'm pretty sure that they used the similar assumptions for as they did for the ADMX. So I'm pretty sure that at least the ADMX ones and ours are kind of on this, you know, making use of the same assumptions. I guess and then I think that sort of the rest of this plot basically came from ADMX. So I think that it's probably true that it's the same assumptions, but I'm not a 1,000% sure. But I think it's pretty. I have reasonable confidence that all of these were done on the same assumptions, just because, again, of my co-authors who are pretty familiar with all of the analyses.
Okay, thank you.
Great. So I think if there's no further pressing question, I think we can thank again Dave for the great talk, for accepting the invitation to talk about this really interesting topic. So thank you again, Dave.
Yeah. Oh, and I forgot to mention, as it happens, if you if you want to hear more about stuff that we're doing, apparently I'm also giving the C2QA colloquium. This is the from one of the NQI centers that's, I guess, based out of Yale. So I'm talking about a totally different topic, which is kind of the sort of some of our kind of many body stuff. So basically using trying to study interacting photons and stuff like that. So if anyone's interested in that kind of thing, it's a different flavor of stuff.
And when is that?
It's this afternoon.
This afternoon. Okay, busy day.
Yeah, I hadn't realized, I think, when I was scheduling that they were both the same day, but luckily they're not actually conflicting. Let's see. I can find out when it is exactly. It's at, I think, 1:30 your time.
Okay.
So.
Excellent.
Yeah.
Okay. So we'll look into that, and we can post it on some of the Slack channels that we have.
Yeah. Cool.
Great. So, well, it was fun seeing you, Dave. Hopefully we can catch up. Otherwise than Team or Zoom in the near future.
Yeah, that would be great.
And I was just talking to Andreas before the Séminaire when he says it up.
Oh, perfect.
Perfect. Okay. Thank you, everyone. Thank you, Dave.
Thank you very much.
All right. Yeah.